Transistors. They are, in my opinion, the most interesting, intricate, tricky, and poorly explained concept in all of beginning electronics. I have spent weeks of my life, spread over the course of months, wading through the water valve analogies and the two diode analogies and the inequality charts and every other doggone thing that the internet and textbooks has thrown at me to try to explain this. Everybody has their analogy. Everybody has their idea that they think is the best way to explain it. And I'm sure for every one of these, someone somewhere has found it to be a perfectly intuitive explanation, but not me. So I have come up with my own. That is what I consider straightforward. It is connected to reality, so it does not use fake nonsense like positive charge carrier holes that are only conceptual in nature. There are positive charge carriers, just not in this case. Holes don't move. It's a hole. So it's grounded in reality, but it doesn't get bogged down in reality. I still treat quantum mechanics like the magic it is, but it also does not use silly mnemonics or other trickery to try and remember it. It's simple. So I hope you like it. We're going to do a short, I promise, review at the beginning, but this is going to be the one be-all and end-all transistor explanation video, and hereafter is how to use them. So if you already understand transistors intimately, then obviously this video is not for you. But if you find them, like I did, to be somewhat understandable but still rather obfuscated, try this out and see what you think. Transistors and diodes are known as semiconductors. A conductor is something that lets current through, and an insulator is something that does not. A semiconductor is something in between. In this case, it means something that can be a conductor or an insulator depending on how it's operated, how you apply voltage and current across it. Semiconductors are composed of layers of N material and P material. N material is negatively inclined but electrically neutral silicon. P material is positively inclined but electrically neutral silicon. This is a diode. These would be touching, I'm just trying to not muddy my markers by drawing over them. So what happens is some of the electrons from this N region wiggle their way over to the P region, leaving behind a positive charge here and creating a negative charge here. This is a high energy state. They don't want to be this way. They attract each other, and there forms an equilibrium where no more wiggle over because there's already enough, based on the construction of this layer. This is called the depletion zone or the depletion layer. This is what gives a diode its property. If you apply the negative side of the voltage to the P and the positive to the N, the depletion zone gets bigger and bigger and bigger and blocks even better until it reaches the edges, when it will conduct and probably catch fire. If you connect positive to the P and negative to the N, the depletion zone shrinks. When it reaches zero, it becomes a wire, and it conducts with minimal resistance. How much voltage that takes is the forward voltage drop. That's where that comes from. So that's just a diode. It is forward biased when you have applied the voltage so it conducts in the forward direction, in the direction of the arrow. That's called forward biasing. You apply enough voltage to get rid of this layer, and through it goes. Reverse bias is just the other way. You've got it backwards. And then unbiased is you're not applying voltage. I'm going to be very clear and say forward biased or not forward biased. Not forward biased does not mean reverse biased. It means reverse biased or no bias, as in you're not even connecting it, or you're not applying enough voltage. If you need 0.7 and you apply 0.2, that's still not forward biased. It has shrunk the layer, but not enough. So I'm going to say forward biased or not forward biased, because when we're talking about transistors, it doesn't matter whether it's partially biased or anything. It's either conducting or not conducting. It's either forward biased or not forward biased. So don't worry about all the other crap. Either you're applying enough voltage to clear the depletion layer, or you're not. There are two types of what are called bipolar junction transistors, BJTs. These are just the normal ones. We'll get into MOSFETs and such elsewhere. You have the NPN type, and you have the PNP type. This is just 3 layers. So unsurprisingly, you have an N material, a P material, and an N material, all touching. The P is usually smaller, but that doesn't matter. Don't worry about how they're constructed. It's just these 3. PNP is just the opposite, a P, an N, and a P. They all have 3 terminals. One here, one here, one here, one here, one here, one here. So this is an NPN transistor, and this is a PNP transistor. And these form depletion layers just like the other. It's just trickier how it works. So one thing you will encounter is the two diode analogy. Now look at it. A diode is a P layer and an N layer. That's a diode. It's a P-N junction. When you have these two together, it's called a junction, and it's two pins. Well, look here. If you take this pin and this pin, N-P, so you've got a diode effectively, not really, effectively, like this. And over here, this pin and this pin, you've got P-N. So you've kind of got a diode like this. This is where it comes from. These two pins, P-N, NP. So this one you've got diodes facing this way, this one you've got diodes facing this way. It's not diodes, it's junctions. This junction is like this junction. This junction is like this junction. Think about junctions, not diodes, junctions. Remember how we can forward bias diodes? Well, that's what we do with transistors. These junctions, we will forward bias the junctions as if they were diodes, and whether we're forward biasing or not forward biasing makes the transistor behave differently. Now, for the moment, we're going to ignore the PNP transistor because it basically is just an NPN in reverse, and at the end, I will be able to give a very quick backward summary. So for right now, we'll just do NPN. And to be fair, NPN is the kind you will usually see. So we have an NPN transistor, NPN, with its three terminals. The one in the middle is always called the base. In the circuit diagram, it's that one. See in the middle? This one is called the collector. This one is called the emitter. The one in the middle is always the base. So the way the transistor works is the base is how you control it. You turn it on and off. Again, there's a billion explanations about amplifiers and all this. We'll get to that when we talk about using them. I'm just talking about how to physically operate them. The base is the on-off switch. If you forward bias the base, it's on. If you do not forward bias the base, it's off. You can operate it in reverse. Don't do that. We'll talk about that later. I'm talking about normally. Normally, you don't operate things in reverse. That's why we call it reverse. Normally, base is on and off. So it's the base emitter junction. You might notice this little arrow. This arrow is the base emitter junction. That is the on-off switch. Why is it called the emitter? I'm not even going to bother to explain. It's supposed to be like source of electrons and sink of electrons, but then for PNP it's reversed. And also it's reversed for conventional current flow because that doesn't match electrons. So basically just memorize collector and emitter. Anything I try to do to explain is just going to make it worse. It's just like saying ground for the negative terminal of a battery. Just go with it. The point is, the base is the control. The base emitter junction, this PN, this effective diode, not a real diode, effective diode. If we forward bias the PN junction like we would forward bias a diode, see, base to emitter, see this arrow? That's conventional current, like this, see? From base to emitter, the arrow. That's what the arrow is. If we forward bias the transistor, the base emitter junction, transistor is on. If we do not forward bias that junction, the transistor is off. So that's step one. Now, if it's on, because if it's off, it's just off. If it's on, it has two modes, active and saturation. That is the other junction. This junction, which is once again, effectively a diode. And here is immediately, it already was, but here's immediately where you see why it's so aggravating to have this two diode analogy. They're backwards. They're opposing each other. What is this nonsense? It's junctions. This is just to make it clear. So you've got a PN junction. This is with it on. If this is off, if base emitter is off, then forget about this. We're not operating it in reverse. We're not doing any fancy crap. If this is not forward biased, it's off. But the base to collector junction, this one, the one that's not got the arrow, if you forward bias that junction, if the base voltage is higher than the collector voltage, then by enough, by the drop of that junction, or whatever your spec sheet for your transistor says. If you forward bias that junction, then this goes into what's called saturation mode. It is effectively a wire, just like a diode, where you forward bias the diode by enough, and then it just lets it through. That's what the transistor does. It begins letting it through. Letting it through how? Collector to emitter. Now, notice the symbol here. The symbol has this bar. So we've got the base on one side and we've got this bar and the collector and emitter on the other. That is to symbolize that effectively the collector to emitter is the wire it's controlling. That we've got this side is the control side and this side is what it's doing. So for example, you would have your transistor and you would have power over here and you would have your ground down here, power up here, and then your load. Now, it works for switching, it works for logic, it works for amplification. We'll discuss all of those. But the point is, this side, the collector emitter, is the stuff that's happening. This side is the control, right? Base to emitter turns it on and off. And then this is the thing that's being turned on and off, or turned up or down. So that's the two sides of a transistor. The stuff happening side, which is up and down, and then off to the side is the control. So if we forward bias the base to collector junction while we are forward biasing the base to emitter junction, then this is in saturation mode and it's just a wire. If we do not forward bias the base to collector junction, that means we're reverse biasing it, it's not biased at all, same voltage on both sides, it's not forward biased by enough, just not forward biased. Then it's in what's called active mode. Then the current through the base to emitter junction, not the voltage, the current. The voltage only matters for the biasing. Transistors, BJTs, are current controlled. The only voltage that matters is whether this is forward biased. Beyond that, it does not have an effect. Now, you'll turn the voltage up to turn the current up, but that's just because of Ohm's law, right? V equals IR. Remember how you have a diode and a resistor, like an LED, and it has a forward voltage drop that's roughly the same all the time, and then the resistor takes the rest. Turn up and down the resistor's value to change the current while the voltage stays the same. So you'll have a voltage you apply and you can turn up and down the resistor to change the current. Or if you're not changing the resistor, you can turn the voltage up and down to change the current while keeping the resistor the same. But that's all that's happening. The voltage only matters to bias this junction or not. After that, it doesn't care, it doesn't notice. Unless you get crazy voltages and then you fry your transistor. You know what I mean. The point is, usually you'll control it by changing the resistance or changing the voltage. What you're controlling is the current. So in active mode, it is not just letting current through. It's letting current through with a throttling effect. For an NPN transistor, the lower the current, the less current is letting through here. The more the current, the more it's letting it through. So that's the magic of a transistor. The base to emitter junction, the one with the arrow, you send current through after forward biasing the junction to turn the transistor on. You forward bias the base to collector, the one without the arrow, in order to put it in saturation mode and make it just a wire. Or you don't forward bias, and then you can turn up and down the current, and that will change the current that goes through the whole thing. I know I'm saying this over and over and over in different ways, but trust me, I have been through this. One of these ways is going to sink in for everybody. So you have the base emitter junction, and you have the base collector junction. If we have the base emitter junction not forward biased, then nothing happens. So over here, nothing happens. Doesn't matter what base to collector is. We're not operating it in reverse. We've just hooked it up normally. Base to emitter not forward biased, doing nothing. Base to emitter forward biased. Base to collector not forward biased. Then it's affected by the current. Low current, low transmission, high current, high transmission. It's a knob you turn up and down. If base to emitter is forward biased, base to collector, forward biased. Saturation, just lets it through. Don't worry about fancy tables, don't worry about anything. It's just each junction is forward biased or not forward biased. And you can find the voltages in your spec sheet or turn it on and measure them. Now, why does this happen? Quantum mechanical magic. Like I said, that is a very advanced topic, and you'll be reading for months to really understand what's going on a physical level. But you don't need to. All you have to remember is those simple binaries. And it's always the one with the arrow. So what about PNP transistors? Currents going from base to emitter, currents going from collector to emitter, and you're just biasing the junctions. Now, PNP, it's just backwards. You've still got an emitter to a base junction, but it's in reverse. Now, if we look at the symbol, the NPN is basically this, right? We've got this arrow pointed here, and the PNP is this. The difference is only the direction of the arrow. You've still got base, collector, emitter, base, collector, emitter. But the trick is, in the NPN transistor, the conventional current is going through the base and out down the emitter, and then it's going through the collector down the emitter. And that's why the arrow is pointing this way. The arrow is always on the base to emitter junction, the control junction, and in the direction of conventional current flow. Backwards, your base to emitter is still the control junction, but the arrow is pointing this way. The current, the conventional current, goes from emitter to base. Because remember, NPN, you've got the transistor, which is effectively two diode junctions, both pointing out. This one is pointing in. P, N, P. A diode is a PN junction. So you've got one going this way and one going this way. Again, they're junctions. They're not diodes. They are junctions, just like diodes. So you can see, in order to forward bias, going from the middle out, you have to apply positive in the middle at the base and negative at the emitter to forward bias it, which means that's the way current flows. This one, it's backwards. This is the base, this is the emitter, and you got to go backwards. You have to apply negative at the base, positive at the emitter, which means current goes that way. Now, why is the symbol like this? Because we write left to right and then we write top to bottom. So we tend to write circuits that way too, to have current kind of going right and down. So the reason for this is just so that we don't have to draw some current going down and some current going up. It's just this flipped. It just flips like this. Same symbol. Sometimes you'll see them flipped like this as well if it suits the circuit diagram. But when you see it like this, it's very simple. This is just the backwards arrow and nothing else changes, but it makes the current go backwards. So it goes from emitter to base and emitter to collector, which is why emitter and collector is so dumb, because it goes backwards for each one. But you never have to remember any of this. The arrow is right there in the symbol. The arrow is the current flow from base to emitter. It tells you which two pins are your junction. You know that the base is the one that's off to the side that looks like it's controlling the other one. And you know the arrow is pointing between the base and the emitter. So now you know which one is the base, you know which one is the emitter, the other must be the collector, and you know which direction the current's going because the arrow's pointing in that direction. So you don't have to remember some mnemonic of what NPN and PNP are. Just look at the symbol and there's the arrow. And then with enough repetition, you'll remember it. But it works the same way. You bias in the opposite direction, but it works the same way. If you forward bias the base to emitter junction, the transistor is on. If you do not forward bias the base to emitter junction, NPN or PNP, then the transistor is off. If you are biasing the base to emitter junction, if you are forward biasing it, then if you are forward biasing the base to collector junction, which is this direction for NPN, this direction for PNP, it's just a different direction, but you're doing the same thing. If you forward bias the base to collector junction, then the transistor is in saturation mode. It'll just let it through. If you are not forward biasing the base to collector junction, then it is going to depend on the current through the base to emitter. How? We'll go into that when we talk about the amplifiers. For right now, just recognize what it's doing, not the details. I hope that helped a little bit. I have gone through this, and just remembering whether or not you've basically got two switches on or off, two little light switches, set you your three modes. The fourth mode is operating it in reverse. Don't do that. So what are we going to go over in the future? Well, there are three operating modes: cutoff, which is off, active, which is amplifying, and saturation, which is just an open wire. That's 0 junctions, 1 junction, or 2 junctions forward biased. The three uses for transistors generally are digital logic. This is for making CPUs. Basically, you've got ones and zeros and ones, trues and falses, highs and lows, and you're doing logic with them to get a result. That's one use. Another use is amplification. You have a small control signal, such as put out by the speaker port of your computer, and you have a large signal that is being put out by your speaker. So the transistor, because your computer's port is not going to put out enough power to power a speaker, especially if it's a really high quality one with subwoofers and all this other crap. That's why your speakers have their own power plug. But the signal is sent from one to the other, and a transistor can be used to control how much is let through in relation to the sound wave. So it can power your speaker, the tiny control signal. The third use is actually similar to that. It's a digital switch. Your Arduino is not going to put out enough power to turn on your 500 blinking LED strip that you've put around your Christmas tree. Of course it will for a microsecond or two, and then you need to buy a new Arduino. But that's essentially the same thing as amplification. You're amplifying it all the way or none at all. But we'll get to that in the future. And then finally, everything comes in threes. There's three arrangements of the wires. So you've got an input signal and an output signal. The input signal is base to emitter. You're controlling the transistor. The output signal is going through the transistor, right? You might think of it that way. So there are 4 pins. You've got an input signal, which is 2 pins, an output signal, which is 2 pins, or wires. 2 wires and 2 wires for 4 wires. And then your transistor has 3 pins. How do you put 4 wires on 3 pins? Well, 2 wires are going to share one. Obviously, 2 wires of the same signal are not going to share the same pin. So 1 pin, whichever, gets 1 input wire. 1 pin gets 1 output wire. The final pin shares them. You can have a common collector, common base, or common emitter. It's basically just which pin has 1 wire from the input and the output. And that determines, unsurprisingly, how the circuit operates. But just one more summary. Transistors are not mystical. Base is the one off to the side of the bar. That is your control pin. Collector to emitter, that's off to the other side of the bar with all the stuff, is your thing that's happening. The arrow always goes between base to emitter junction. That is your control junction. The arrow goes in the direction you apply the bias. NPN, you've got PN, so you're going this way. PNP, you've got NP, so you're going this way. But you don't need to remember that because you've got an arrow that's telling you that. So the arrow is the direction you apply the voltage. Your spec sheet is how much voltage, or turn the voltage up until it turns on, and then write it down. If you forward bias the base to emitter junction, this way or this way, the transistor turns on. If you do not forward bias the base to emitter junction, the transistor does not turn on. The base to collector junction, if you forward bias it this way, then the transistor is in saturation mode. If you do not forward bias it, then the transistor is in active mode. That's the amplifier mode. Collector to emitter is the current. And again, the arrow shows you base to emitter, so the other current has to be going the same way. You can't have forward and backward current on one pin. So if you know the arrow is pointing this way, base to emitter, you know collector to emitter is also that way. Same here. The arrow is pointing this way, emitter to base, so the current is emitter to collector. And it works if you flip the symbol upside down as well. You can see emitter to base, emitter to collector, just go by the arrow. Don't overcomplicate it. Just think of two junctions, think of three ways to turn them on and off, and there you go. And as a reminder, these are current controlled. Forward bias or not forward biasing, the voltage does not matter after that. You forward bias with 0.7, 0.3, whatever volts, according to whatever transistor you're using. If you forward bias, the junction is biased. If you don't, it's not. And after that, it's current. And MOSFETs, of course, don't work that way. But we'll worry about that later. So I think this is a perfectly clear explanation, but it's going to take a little while for it to sink in. You can feel free to refer back to this video or just take notes or ask me questions in the comments if you'd like. But as you work with transistors, as I make videos about transistors, I will try to point out these things as we go. Try to point out the fact that I'm biasing or not biasing junctions, and I hope that'll make it sink in. So forget about your water analogies, forget about your two diode analogies, forget about your inequality tables. Bless SparkFun's little heart, but even they, the ones that are the most newbie-friendly on all of the internet, still fall in this trap, where they say, oh, it's like two diodes, but not really, don't do that, in the same paragraph. And then they have their inequality tables that completely ignore the actual forward bias voltages, and then later on, they're like, oh, and now we have this. And like, you just explained it, now you have something new. Just start with this, keep it simple. Bias or not bias. So I've done enough talking for now. Next video, we'll actually do something. Until then, be seeing you.